I have spent most of my life in conversation with nature, asking her questions, designing experiments, puzzling over her answers. And if there is one thing I have learned with absolute certainty, it is this: nature never commits. She refuses, at the most fundamental level, to declare herself definitively. She keeps her options open in a way that defies every intuition we have built from our everyday experience with the macroscopic world. This may sound abstract, even mystical, but I assure you it is either. It is the most concrete, experimentally verified truth we have discovered about the physical world. And it emerged, piece by piece, from the revolutionary developments in physics during the first decades of the 20th century, developments in which I had the privilege to play a central role. Let me take you back to the beginning of my journey into this peculiar truth. When I arrived at Ernest Rutherford's laboratory in Manchester in 1912, physics was in the midst of a crisis, though not everyone recognized it yet. Rutherford had just discovered that the atom consisted of a tiny, dense nucleus surrounded by electrons. This was a magnificent insight, but it created an impossible situation. According to the electromagnetic theory of James Clerk Maxwell, which had been confirmed in countless experiments, an electron orbiting a nucleus should continuously radiate energy and spiral inward, collapsing into the nucleus in a fraction of a second. Classical physics gave us a clear, committed answer: atoms cannot exist. And yet here we were, made of atoms that had persisted for billions of years. Nature was already showing us that she refused to commit to the predictions of our classical theories. My solution in 1913 was to propose that electrons could only occupy certain specific orbits where they mysteriously did not radiate energy despite being in accelerated motion. An electron could jump between these orbits, emitting or absorbing light in the process, but it could not exist between them. This worked mathematically, it explained the spectrum of hydrogen beautifully, but I knew even then that something deeper was at play. I had not explained why electrons behaved this way. I had simply imposed rules that matched experimental observation. What I did not fully understand yet was that I was witnessing the first hints of nature's fundamental refusal to commit, her insistence on maintaining multiple possibilities simultaneously until forced to choose. This truth would only become clear with the full development of quantum mechanics in the 1920s. The revolution truly began when Louis de Broglie proposed in 1924 that if light could behave as both wave and particle, then perhaps matter could too. Perhaps electrons were not simply particles but also possessed wave-like properties. This was a startling suggestion, but it was soon confirmed experimentally. Electrons could produce interference patterns, just like waves. They could diffract around obstacles. They exhibited wavelengths inversely proportional to their momentum. Then came Erwin Schrödinger's wave mechanics and Werner Heisenberg's matrix mechanics, both developed in the mid-1920s. These two formulations looked completely different mathematically, but they were proven to be equivalent. And both of them did something revolutionary. They described quantum systems not in terms of definite properties but in terms of probabilities, in terms of all possible states existing simultaneously until a measurement is made. The Schrödinger equation, which governs how quantum systems evolve, does not tell you where an electron is. It tells you where it might be, with what probability. Before you measure the electron's position, it exists in what we call a superposition of all possible positions, each weighted by a probability amplitude given by the wave function. This is not because we are ignorant of where the electron really is. It is because the electron does not have a definite position until we measure it. Nature has not committed to a specific location. Let me emphasize this because it is so counterintuitive. The electron is not secretly located somewhere specific, waiting for us to find it. It genuinely does not possess a definite position. It exists in a state of possibility, of multiple potentialities held in suspension. Only when we perform a measurement does nature commit. Does the wave function collapse? Does the electron manifest in one particular location? This is what I mean when I say nature never commits. She maintains superpositions, she holds contradictory possibilities in simultaneous existence, she refuses to declare definite values for properties until observation forces her hand. And this is not a philosophical position or an interpretation, it is what the mathematics tells us, and what every experiment confirms. Werner Heisenberg, working with me in Copenhagen, discovered the uncertainty principle in 1927. This principle makes explicit what is implicit in the quantum formalism. Certain pairs of properties cannot both have definite values simultaneously. The most famous example is position and momentum. The more precisely you know an object's position, the less precisely you can know its momentum, and vice versa. The product of the uncertainties in these two quantities must be at least on the order of Planck's constant divided by 4 pi. This is not a statement about measurement error or the limitations of our instruments. It is a statement about nature herself. Nature does not commit to definite values of position and momentum simultaneously. She cannot, because these properties are complementary, mutually exclusive aspects of quantum reality. I developed the concept of complementarity to express this fundamental feature of quantum mechanics. Complementarity means that a complete description of quantum phenomena requires mutually exclusive experimental arrangements. You can measure position or you can measure momentum, but you cannot measure both with arbitrary precision in the same experiment. You can observe wave-like behavior or particle-like behavior, but not both simultaneously. These complementary aspects are both necessary for a full understanding, but they cannot be accessed at the same time. This is nature's refusal to commit in its purest form. She will show you the wave nature of an electron if you design an experiment to see waves. She will show you the particle nature if you design an experiment to see particles. But she will not show you both at once. She adapts to the question you ask, but she never gives you the complete picture in a single snapshot. The double-slit experiment illustrates this perfectly. When you fire electrons one at a time at a barrier with 2 slits, they build up an interference pattern on a screen behind the barrier, just as waves would. Each electron somehow goes through both slits simultaneously and interferes with itself. The electron exists in a superposition of going through the left slit and going through the right slit. Nature has not committed to either path. But suppose you place detectors at the slits to determine which path each electron takes. The moment you do this, the interference pattern disappears. You see electrons going through one slit or the other, building up 2 distinct bands on the screen, exactly what you would expect from particles. By forcing nature to commit to which slit the electron went through, you destroy the superposition, you eliminate the possibility of interference. This is not sleight of hand or experimental artifact. It is the fundamental character of quantum reality. The electron genuinely goes through both slits when you are not looking. It exists in a superposition of both paths. Only when you observe does it commit to one path or the other, and in committing, it loses the ability to interfere with itself. I remember long discussions with Albert Einstein about these matters. Einstein had contributed enormously to quantum theory in its early days, but he could not accept what the theory was telling us about reality. He believed deeply that nature must have definite properties independent of observation, that particles must follow definite trajectories whether we observe them or not, that the probabilities in quantum mechanics reflected our ignorance rather than nature's fundamental character. God does not play dice with the universe, he famously said. To which I replied, Einstein, stop telling God what to do. But this exchange, often quoted, masks the depth and seriousness of our disagreement. It was not about theology but about the nature of physical reality, about whether determinism was fundamental or whether probability was woven into the fabric of nature itself. Einstein devised numerous thought experiments to try to show that quantum mechanics was incomplete or inconsistent. At the Solvay conferences, he would present these challenges, and I would spend hours working through them, showing where they failed to undermine quantum mechanics. Each time, the theory held firm. Nature's refusal to commit remained unshaken. The most profound challenge came in 1935 when Einstein, working with Boris Podolsky and Nathan Rosen, published what became known as the EPR paradox. They considered 2 particles that had interacted and then separated by a large distance. According to quantum mechanics, these particles become entangled. Their quantum states are linked in such a way that measuring one particle instantly affects the state of the other, regardless of the distance between them. Einstein argued this was absurd. Either quantum mechanics allowed faster-than-light influences, violating special relativity, or the particles must have had definite properties all along, determined at the moment of interaction, and quantum mechanics was simply an incomplete description. He called the apparent instantaneous influence, Spukhaft-Fernwirkung, spooky action at a distance, and considered it a reductio ad absurdum of quantum mechanics. But Einstein was wrong, though it took decades to prove it definitively. The particles in an entangled state genuinely do not have definite properties individually. The two-particle system is in a superposition of correlated states. Nature has not committed to definite values for either particle. Only when you measure one particle does nature commit, and this commitment immediately determines what you will find if you measure the other particle, no matter how far away it is. This is not because information travels between the particles. It is because the particles never were separate, independent entities with definite properties. They form a single quantum system, a unified whole that cannot be broken down into independent parts. The entanglement is not a connection between them but a reflection of their fundamental inseparability in quantum terms. John Bell, working long after my death, proved a remarkable theorem that settled the matter. He showed that any theory based on local realism, the idea that objects have definite properties independent of observation and that influences cannot travel faster than light, must satisfy certain mathematical inequalities. Quantum mechanics violates these inequalities. And when experiments were performed, starting in the 1970s and continuing with ever greater precision, nature sided with quantum mechanics. The Bell inequalities are violated. This means nature truly does not commit to definite values for quantum properties until they are measured. There are no hidden variables determining everything in advance. The superpositions are real. The probabilities are fundamental, not a reflection of ignorance. Nature keeps her options open at the deepest level of physical reality. Now I want to address what this means for causality and determinism, because this is often misunderstood. Quantum mechanics is perfectly deterministic in one sense. The Schrödinger equation describes how the wave function evolves over time with complete determinism. If you know the wave function at one moment, you can calculate it at any future moment. There is no randomness in this evolution. The indeterminism, the randomness, enters only at the moment of measurement, when the wave function collapses from a superposition to a definite state. We can calculate the probabilities for different outcomes with extraordinary precision, but we cannot predict which specific outcome will occur in any individual measurement. Nature makes this choice, and she makes it randomly, not based on any hidden variables or predetermined plan. This bothered Einstein tremendously because it seemed to make nature capricious, arbitrary. But I saw it differently. The randomness of quantum measurement outcomes is not a failure of explanation or a gap in our knowledge. It is a fundamental feature of nature, as basic as the conservation of energy or the speed of light. And it is intimately connected to nature's refusal to commit before she must. Think about what it would mean if nature did commit in advance. It would mean every quantum particle had definite values for all its properties at all times, whether we measured them or not. But we know from the uncertainty principle and from Bell's theorem that this is impossible. Properties like position and momentum cannot both have definite values. Complementary aspects cannot both be manifest simultaneously. Nature cannot commit to everything at once because the properties themselves are incompatible. So nature does something remarkable instead. She maintains superpositions, she keeps multiple possibilities alive simultaneously, and only when forced by measurement does she collapse to one outcome. This is not indecision or incompleteness. This is the optimal solution to an impossible problem. It is how nature manages to be consistent while respecting the incompatibility of complementary properties. Let me give you another way to think about this. In classical physics, we imagine that objects have intrinsic properties that exist independently of observation. A baseball has a definite position and a definite velocity whether anyone is looking at it or not. These properties are out there in the world, and measurement simply reveals what already exists. But in quantum mechanics, properties are not intrinsic to objects alone. They emerge from the relationship between the quantum system and the measuring apparatus. An electron does not have a position in isolation. It has a position relative to a measurement context, a specific experimental arrangement designed to measure position. In a different experimental context designed to measure momentum, the electron does not have a definite position, it has a definite momentum instead. This is what complementarity really means. Properties are not absolute features of objects, but relational features that depend on the entire experimental context. And because different contexts are mutually exclusive, you cannot simultaneously set up an apparatus to precisely measure both position and momentum. Nature cannot commit to both properties at once. I want to emphasize that this is not idealism, not a claim that reality depends on consciousness or human observation. The measuring apparatus need not be conscious. A simple detector, a photographic plate, any physical system that interacts with the quantum system in a way that records information and amplifies it to the macroscopic level, constitutes a measurement. The key is the interaction between the quantum system and the classical measuring device, not the presence of a conscious observer. But there is something profound here about the role of information in physics. Before quantum mechanics, we thought of information as something external to physical processes, something we collected about nature but that played no fundamental role in nature herself. Quantum mechanics tells us differently. Information is central. The distinction between committed and uncommitted states is fundamentally about what information has been extracted, what questions have been answered, what possibilities have been eliminated. When nature maintains a superposition, she is keeping information latent, potential, not yet actualized. When she collapses the wave function through measurement, she is making information manifest, transforming potentiality into actuality. This is not just how we describe quantum systems. This is how quantum systems actually are. The measurement problem, as it is called, remains one of the deepest questions in quantum mechanics. Exactly when and how does the wave function collapse? What counts as a measurement? Where is the boundary between the quantum system and the classical measuring apparatus? Different interpretations of quantum mechanics give different answers. In the Copenhagen interpretation, which I helped develop, the collapse occurs when a quantum system interacts with a classical measuring device. The boundary between quantum and classical is somewhat fuzzy, somewhat pragmatic, defined by what we treat as the measuring apparatus rather than the measured system. This bothered many physicists because it seemed to make the boundary arbitrary. Hugh Everett proposed an alternative where wave functions never collapse. Every possible outcome of a measurement occurs, but in different branches of a splitting universe. In this many-worlds interpretation, nature commits to everything by creating separate realities for each possibility. I must say, while this solves certain conceptual problems, it seems profligate beyond measure. Other interpretations exist: pilot wave theories, consistent histories, objective collapse models, each with its own way of handling the measurement problem. But regardless of interpretation, the experimental facts remain the same. Nature behaves as if she maintains superpositions until measurement. She behaves as if she refuses to commit until forced to do so. And this refusal to commit has profound consequences for what we can know. It is not just that we cannot know both position and momentum precisely. It is that nature herself does not contain this information. There is nothing to know. The information simply does not exist until we choose what to measure and actually perform the measurement. This is a radical departure from classical physics, where we assumed that complete information about the present state of the universe, combined with the laws of physics, would allow us to predict the future with certainty. Laplace famously imagined a demon with such complete knowledge, able to foresee all future events. But quantum mechanics tells us this is impossible even in principle. Nature does not contain the complete information that Laplace's demon would need. She keeps some information in a state of potentiality, uncommitted until observation. I find this beautiful rather than troubling. Nature is not a clockwork mechanism, predetermined from the beginning of time. She is creative, generative, continually bringing forth new information through the process of quantum measurement. Each observation is not just a passive recording of what already existed but an active participation in creating definite reality from quantum possibility. This has implications far beyond fundamental physics. In chemistry, the fact that electrons in atoms exist in superpositions of different states, that nature does not commit to definite electronic configurations until measurement, is essential to understanding chemical bonding, molecular structure, reaction rates. The whole of chemistry emerges from this quantum indeterminacy. In biology, quantum effects play roles we are only beginning to understand. Photosynthesis appears to use quantum superposition to explore multiple energy transfer pathways simultaneously, finding optimal routes with remarkable efficiency. Some theories of olfaction suggest that the nose distinguishes molecules through quantum tunneling effects. The mutation process that drives evolution depends on quantum uncertainties at the molecular level. Even consciousness, that most mysterious phenomenon, may have connections to quantum mechanics, though we must be very careful here not to make claims beyond what evidence supports. Roger Penrose and others have speculated that consciousness might be related to quantum collapse processes in the brain. This remains highly speculative, but it points to how deeply quantum indeterminacy might be woven into the fabric of reality, even at levels far removed from atoms and electrons. The technological implications are equally profound. We are now developing quantum technologies that explicitly exploit superposition and nature's refusal to commit. Quantum computers maintain superpositions of many computational states simultaneously, effectively exploring multiple solution paths at once. Only at the end of the computation does nature commit to an answer. This allows quantum computers to solve certain problems exponentially faster than any classical computer possibly could. Quantum cryptography uses the principle that measuring a quantum state necessarily disturbs it. Any eavesdropper trying to intercept a quantum key would collapse the superposition in a detectable way, alerting the legitimate users. This provides theoretically perfect security, guaranteed by the laws of physics themselves. Quantum sensors exploit the extreme sensitivity of quantum superpositions to external influences, achieving precision impossible with classical devices. Quantum metrology promises to redefine our fundamental standards of measurement. All of this works because nature refuses to commit, because she maintains delicate superpositions that we have learned to prepare, manipulate, and measure. Looking back over my career, over the decades I spent wrestling with these questions, I am struck by how resistant we are to accepting what nature tells us. Our intuitions, built from everyday experience with macroscopic objects that do have definite properties, rebel against the quantum world. We want to believe in an objective reality out there, independent of observation, with all properties definitively fixed whether we look or not. But nature is not obligated to conform to our intuitions. She is what she is. And what she is, at the deepest level we have been able to probe, is fundamentally probabilistic, fundamentally uncommitted until measurement forces commitment. This is not a failure of physics, or a gap in our knowledge. It is a discovery about reality itself, perhaps the most important discovery of 20th century physics. I spent many hours in debate with Einstein, with Schrödinger, with others who hoped to preserve classical determinism, who believed quantum mechanics must be incomplete. I understood their discomfort. I felt it myself in the early days. But the evidence was overwhelming. Experiment after experiment confirmed the quantum predictions. The mathematics was consistent and elegant. And no viable alternative emerged that could match quantum mechanics' empirical success while preserving classical intuitions. So I learned to embrace the strangeness, to see it not as a defect but as a revelation. Nature never commits because committing fully would be inconsistent with the uncertainty principle, with complementarity, with the fundamental structure of quantum mechanics. By refusing to commit, nature achieves something remarkable. She maintains consistency while respecting the incompatibility of complementary properties. She allows for a world rich enough to support atoms, chemistry, life, and consciousness. She provides the substrate for genuine novelty and creativity in the universe. This is not the endpoint of physics. We still seek to unify quantum mechanics with general relativity, to understand quantum gravity, to probe the nature of dark matter and dark energy, to explain the values of fundamental constants. But whatever future theories emerge, they will have to preserve the lessons of quantum mechanics. They will have to incorporate nature's refusal to commit, her insistence on maintaining superpositions, her probabilistic character at the fundamental level. The universe is not a machine running on predetermined tracks. It is something far more subtle and wonderful. At every quantum event, at every measurement, nature makes fresh choices, collapsing superpositions into definite outcomes in ways we can predict probabilistically but not deterministically. The future is not written. It emerges moment by moment from quantum potentiality. This is what I learned from a lifetime studying the atom, from decades of thought experiments and philosophical debates, from watching as experiment after experiment confirmed what the mathematics told us: nature never commits until she absolutely must. And in that refusal, in that maintenance of possibility and superposition, lies the key to understanding quantum reality and perhaps to understanding the creative, open, genuinely novel character of the universe itself. We must have the humility to accept what nature tells us, even when it contradicts our deepest intuitions. We must have the flexibility to adapt our thinking to accommodate her truths rather than insisting she accommodate our preconceptions. And we must have the courage to follow the mathematics and the experiments wherever they lead, even into territories as strange as quantum superposition and fundamental indeterminacy. This is the lesson I hope to leave you with: that nature's refusal to commit is not a mystery to be solved or an incompleteness to be remedied, but a fundamental truth to be accepted and appreciated. It is how reality works at the deepest level. And far from being a limitation, it is the source of richness, complexity, and creativity in the universe. We live in a quantum world, and that world is more beautiful, more subtle, and more wondrous than we ever imagined before we learned to listen to what nature was telling us.